molecule. Gives you an enormous amount of information about about any properties of these systems that you're trying to predict. We just chatted about this for about an hour, right? So that's sort of the first aspect. But the part of it, I sort of personally never found that to be so essential, and we'll maybe can have a discussion about that. It would be interesting to have. I was always more interested in the groups, right? So that's the second aspect in this. You have various group actions. It's the moment you have geometric objects, there are natural groups that act on them. And how do you build these group actions into your models? That is the main purpose of what I'll talk about. And nothing I'll talk about will be deep. So I'm actually, admittedly, I'm not an enormous fan of deep models. I personally work mostly on linear models or very shallow models. And that will be the focus of this talk. And if I can manage to fit it in somewhere in between, I'll also talk briefly about the consequence of the ideas you need for linear models for the deep models, because there are obvious connections. The ideas in all of these are sort of the same ideas come up again and again and again. So it's always the same concepts. Okay, so back to atoms.
That's really been focused on my very long time.
Check.
Different aspects of this course training mostly, right? So that the context you can think about is there's some simulation you're trying to perform. It's on a scale here, but I can't really large scale simulations slide. But think of it, hundreds of thousands, millions of atoms.
Smaller systems, but very long time scales. And what kind of simulations do you want? I don't know. It depends on your context. Could be molecular dynamics, could be just predicting a structure by energy minimization, transition state search, or just sampling from some invariant measure. There are lots of tasks in there, and in all of these, you need to choose what is your interaction model, right? What is the energy, the potential energy for your system that you start with, and that will be the topic of the talk, really. Where does that model come from? And so I was told that most people here might be interested in interatomic potentials, but not everybody. And so I'm going to spend at least just very briefly to give a background on that. Right? So if you're a modeler, you'll say, okay, at least for certain materials properties that I'm after, let's say I totally trust density function theory. If a chemist, you wouldn't, but that's again your choice of sort of the model. And if my system, if I could use that, I would, but I can't because I have a large scale simulation, right? And so you can say, okay, can I know up here, right? So continuum, coarse grain, that it doesn't give me the resolution, so those are out the window. And so that the natural level of theory to use here is normally the level of interatomic potentials. And are those really good enough, right? So what are those models? What are interatomic potential models? This is a class of models that sort of, it's a bit older, but really, sort of, I think 80s onwards, they became really dominant, where you choose a very, very simple, maybe empirical, maybe inspired by chemistry, maybe sort of semi-rigorously derived functional form for the interaction between the particles, right? So R, that would be the list of all the particles in your system. And then, for example, in this particular model, let's say it's a Stillinger-Weber model, you put a pair interaction between any pair of particles, and then you say, okay, in silicon, I know exactly what the angle is between two bonds, and so I'm going to put another term here, right, V3, that puts basically a spring on the angle, more or less, right? And now I parameterize that, right? So now I have two functions to parameterize, a pair potential and a three-body potential. Those are really low dimensional. I only need a handful of parameters for those. I fit them to some experiments. Maybe I have some theoretical observations I can make to which I can fit those parameters. And that gives me a parameterized potential energy landscape. And so what's and you can actually do quite well. So simple systems, for example, elemental materials, this has been enormously successful. Even for complex molecules, as long as you don't care about reactions, that's been enormously successful, and there was a Nobel Prize for that, even, right? So why not? But this is painstaking work. It takes months and years to develop these potentials, and and once you get to too much complexity, too much chemical complexity, they just cease to work well. And so pretty much nowadays, what we're trying to do is replicate that process, automate it and scale it, right? So we just take a universal approximator for the object we're after, in this case, the potential energy surface for the material or molecule, and fit the parameters to whatever data we get our hands on. Yeah, I don't think there's too much more I have to say about this. Okay, why are we doing this? Well, I sort of mentioned it's the complexity of the problem increases. But you know, even though, let's say for elemental materials, you can get quite far with empirical potentials, you can't get everything. And so this is a sort of a tour de force, really. It took them 5 years to develop this graph. Garbacciani, he's really my main collaborator in this field. I think he's spoken here a few months ago, so you might even have seen this figure before. So what you can see here is a list of material properties on silicon that you want to predict, and there's a list of potentials for silicon that you might want to use for that. And what you see really are all of these potentials get a few properties at good accuracies, but this only that one here, arguably EDIP, okay, but let's say only gap here is the one that gets high accuracy on all of them. And that's because that is in this machine learned class of potentials, and they have the advantage that if you want to add more physics, you just add it in, right? You can keep adding physics at a cost of large and expensive models, right? So if you compare this, say, to the Stillinger-Weber model that I showed you before, you're on the order, you're usually well below a microsecond per atom for the prediction, and now you add milliseconds and above, right? So this, have we sort of beat this cost of DFT yet? I don't know, but this is what we're working on. How can we make this as efficient, as flexible, as automated as possible, right? And so my personal interest is really not the ML at all. I think of this as a coarse graining problem. You have a reference model, the electronic structure model, you're integrating out the electronic degrees of freedom, you have a coarse grain model. How can I best represent that? And as a mathematician, I've always been more interested in the more theoretical aspects of that, right? So in this process, can I really take care that I understand every little step along the way? Yeah. So what I want to do today is, first of all, talk about how we're building models, the atomic cluster expansion framework. I'll describe that in a little bit of detail. Then I'll see how much time I have to give a few examples, not just interatomic potentials, but completely different things that you can do with the same framework, to more for entertainment maybe. And then at the end, again, depending on how slowly I'm talking, I'll talk a bit about the workflow that we use in order to build real models that do interesting things, robust models. Yeah. Okay. So as I said, I'm not actually thinking this of a machine learning problem, more as a modeling problem where machine learning helps us. And so I'll start with the modeling step. And the first modeling step is that you can't parameterize the entire potential energy surface at once. You have to, right? And so for example, you know, if you did this, let's say you're thinking of simulations with 100,000 atoms, you couldn't generate data for that, right? So you know, people who do interatomic potentials, the next step is going to be trivial for you, but people who don't, for this, it's a non-obvious step. And I like to show it again and again because and emphasize how not obvious it actually is until you've seen it, is that in order to get past that, you need a spatial decomposition of total energy. It's not only not obvious, but also not trivial why such a spatial decomposition should even exist. Yeah. So most of the time we're just postulating that. We're hoping for the best when we do this. And so the idea is that you write the total energy as a sum of site energies. Each site energy depends on atomic environment. Right? So the red circle would be such a typical atomic environment. So very, very small neighborhoods of atoms, and the energy contribution from each site is extracted just from those neighborhoods. And the point now, for the purpose of machine learning, is that instead of parameterizing this ridiculously high dimensional object, you're parameterizing a much lower dimensional object now. And because it's spatially small also, you can parameterize this from small structures, but then make predictions on large structures. That's the important point here. Okay, so as I asked, is this actually justified? And that was one of the early questions on this topic of machine learned potentials that always interested me. And Jack Thomas and Faisal Nazar, two former PhD students who worked on that. And so what they did is they identified a range of electronic structure models for which we can actually prove this, saying that actually this electronic structure model, EQM, the total energy, has such a spatial decomposition. And moreover, but so in these electronic structure models, the interaction range is infinite, so it can't be quite like that. So in fact, the way you have to then quantify this is you have to say that you can approximate that quantum site energy with an actual site energy that has a finite interaction range plus an error. And then quantifying those errors, or at least getting them qualitatively sharp and so on and so forth, that all of that can be done not in full generality, but when you make sufficiently strong assumptions. Yeah. And what's almost more interesting than proving this is understanding how the assumptions break and how you change your models. But that's a longer discussion that I'm not going to get into today. Okay. Still, you still have a problem here in that these site energies are really not that low dimensional, right? So 30 to 100 dimensions is still not so easy to parameterize unless you put in more information. The next part of this, the sort of modeling framework kind of thing, is that they're not actually functions defined in a fixed dimensional space, because when you look at different sites, you have different number of particles in each. So you really best not treat them as functions on some Euclidean space, but actually they're set functions. So the inputs are not, it's not a tuple, but it's a set of atoms, or a multiset to be precise. And finally, the last part in this, and that's sort of where the other part where the geometry comes in, is they have to remain invariant under isometries. And because if you don't do this, then you get models that are qualitatively wrong. Certain conservation laws fail, and well, nobody will use your models. Let's put it that way. Okay, so that's the context. I'd like to parameterize these site energies, but more generally speaking, I'd like to parameterize set functions that are invariant under certain group symmetries. Yeah. And exactly the same problem comes up all over the place. So on this scale, when you think about coarse graining in the scale of materials modeling or molecular modeling, you see this here, for example. So we just talked about hamiltonians for half an hour or so. In this case, these are again, these hamiltonians are now operator valued functions of sets, and they're no longer invariant, they're equivariant, but the principle is the same. And this is something that I had a lot of fun with as well in the similar context. If you're trying to, let's say, construct coarse-grained dynamical systems, right? So they have a coarser resolution of your particle systems. You have to parameterize the free energy or potential of mean force. That's the same thing as before, right? But you also have to parameterize this friction operator. So again, you have an operator value covariant, but it's again a set function. It depends. The input now are sets of particles. Yeah. And more recently, I started playing at this scale here, and we started parameterizing wave functions with the same methodology that I'm about to show you. And in this case, they're not technically sets, but you have a permutation invariance in those. If you take a backflow ansatz for wave functions, then you have a fixed number of input particles, because you're interested for a wave function for a fixed number of electrons. But the permutation invariance brings this exactly into the same context. You treat them as sets or multisets, and you're back in the same setting. So and then even more recently, I stumbled on a very interesting undergraduate student who says, "Oh, I would like to use all of this for jet tagging." And so we started going further down here into elementary particles, and and again you end up with certain operations that are acting on sets of particles that are invariant, in this case now under Lorentz group symmetries. And again, you're back in the same picture. And you could keep making that list longer and longer and longer. So I'll maybe skip this, but we'll come back to that if I have time later. Yeah. So my point is that I started by introducing this idea with site energies for interatomic potentials, but this task of parameterizing set functions that have an additional invariance under some Lie group symmetry is extremely generic. It comes up all over the place. No matter where you look, you'll find interesting problems that require that specific task. And so I wanted to abstract all of that away now and show you briefly what's the abstract setting I'm thinking of. Okay, so the setting is you have some particle system. I'm calling this capital X, right? The input in your model will be this set or multiset of particles. They live in some abstract domain omega. Okay, you can think of it as a point cloud if you wish, and you're trying to parameterize functions f of x that take as input these sets. Yeah. Now, there's one important point I do want to make here. The scale I'm interested in, right? So how many particles are we thinking of? Typically tends to at most hundreds. And what that means is you're definitely not in an order one regime. You really need to think about how to deal with the dimensionality here, the large number of particles, but also you're nowhere near enough in terms of number of particles to go to mean field limits. So just coarse grain that away, it's not going to play. You really need the resolution of the individual particles for many, many, many reasons. Yeah. Okay. This is sort of a summary of what kind of particle systems I'm interested in, but I'm just going to leave this up and move on to that now. So again, we're interested in general group invariance. Right? So this function f, if I apply a group action on the individual particles, it must remain invariant under that group action. And the typical groups we're interested in are orthogonal group and Lorentz group. And then one student I'm working with a lot is also interested in quantum field theory, and so he's getting into those ones. And so so there are but also product groups, right? So for example, there are many scenarios where you want products of isometry groups and so on. So it gets increasingly complex, and that's why you just abstract it away and say you have a group. Okay. So very briefly, what I'm not doing is, this would be sort of the early days in this field. You would say, okay, I'm going to construct a feature vector, I'm calling that B here, that incorporates all the information I have, and then I stick it into a universal approximate, and I'm done. We won't do that. We'll go back further in time, much further, to the times of polynomial regression. What I want to show you is an approach how with basically classic polynomial regression plus a little bit of group theory, you end up with this parameterization of group invariant set functions. It's sort of a nice connection that I like very much. For interatomic potentials, ideas along these lines, you can find Bowman and Brahms very, very early days. They use completely different techniques. But then, for example, Aidan Thompson, what he's done is very much a precursor to what we do. Alex Shapeev's moment tensor potentials are very much related to what we're doing, and Ralph Drautz's atomic cluster expansion. That is basically the starting point. Yeah, that's from that paper we've built everything. Also the other thing to mention, the two main ideas we need in this are very much related to deep sets, for those of you who've worked with that, and to equivariant networks like Tess is working on, for example. And yeah. Okay. So now I need one more modeling step. So the first modeling step was when I said I talk about interatomic potentials, I go from total energies to site energies, right? That is really a modeling assumption, and I said we can justify it maybe, but it was sort of still a modeling step. And the second one now, this is more generic. This is not restricted just to interatomic potentials. Is how we deal with this situation of having many particles. Yeah. So I mean, you don't even have to think of this as, okay, I have too many particles, I don't know how to parameterize. You can just start from saying, okay, I have a set, I don't even know how to parameterize a set function, right? Let's go back a few years before there were deep sets and before there were all of these ideas around, right? But back then, the first thing you would do is do something like this. And depending now who you are, you call this HDMR or ANOVA expansion or cluster expansion. Different fields give it different names, and it's always the same idea. You're saying, okay, I approximate my function f of x. X is the set. by a function fn, which says that only up to n particles can interact at the same time. So I expand into a constant term, a one-body term, a two-body term, up to an n-body term, and then I stop. And by doing so, I've done two things. First of all, I created a parameterization where these individual pieces in here are fixed dimensional, and so those I can now parameterize by whatever method I like. And secondly, if I can manage to truncate this at an n that is much lower than the typical number of particles I have in my system, then I've made my model much lower dimensional. Okay. Okay, so now what do I know about each of these fn's? Well, they're defined on the same space as my particles, right? Tensor product space, and they're symmetric, right? Under exchange of particles, and they should also inherit the group invariance. I didn't write this down here, but that should be in there. Okay, so now, does this thing converge, right? That's, again, I'm a mathematician. I want to make sure every step I make is systematic. And when you're thinking, again, depending on the field you're in, what you're working on, people will tell you, yeah, of course it does, or no, we know it doesn't. And in the case of interatomic potentials, you get both answers, depending on who you ask. And there's sort of a very conflicting folklore in this. And so well, this was, again, my student Jack Thomas, who this was part of his PhD thesis, again, to try and figure out what can we prove about this. And again, for certain specific electronic structure models, we can actually prove that this many-body expansion does converge, and it converges fast. And we can explain why it does, and so on. And maybe for the people who are interested in chemistry, the reason many people think it doesn't converge is because they think of the vacuum cluster expansion. They think of this term as being the energy of a cluster in vacuum. And then indeed, it does not converge. That is true. But if you think of this as the energy of a cluster in the right chemical environment, then you get this result, right? So there are various restrictions in this result that basically formalize what I just said. Right, that this is only true as long as the configurations you're sticking into your model are in the right chemical environment. But in general, it depends very much on the context you're in, whether or not you can say anything rigorous about this, or even formal. Okay, so here's now still, there's a problem remains, right? The cost of the sum here is exorbitant. And if you're allowed to truncate here, you're fine. You don't worry about it. But we don't. We want to make this systematic, so we need to let n become as large as we want. And 3, 4, 5, even that, this becomes an expensive sum. And so we have to deal with that somehow. And how do you deal with that? That for me is the atomic cluster expansion. That for me is the method that showed how to work efficiently with this many-body expansion. Yeah. And the idea is that you first do something dumb. You say, okay, what I've done here is I try to do as much as I can because of the permutation invariance. I only need to sum over unique clusters. That's why I write J1 less than ... Let me ignore that for a second and say, okay, let me just sum over all clusters. And actually, I'm doing something even more seemingly strange. I sum over clusters where atoms are repeated. And what that does is it changes the summation from a simplex to a tensor product space. Yeah. And once you have tensor products, a lot of good things happen. Yeah. That's sort of the key. This is the key step. Once you see that, everything kind of just follows. So now we have that. We parameterize not the f's, but the u's. And what you do is you take you have a tensor product sum. You perform a tensor product parameterization of these u's, right? So here's what that is. I approximate this u by some, it could be a polynomial. It doesn't actually have to be, right? So then here's my tensor product basis. This is a basis that parameterizes single particle functions. This tensor product space parameterizes many particle functions. And that summation over tensor product domain interacts very well with that tensor product basis. And you exchange sums and products back and forth and back and forth. And you end up with this model, right? So I've now taken the sum of the j's all the way inside and becomes a single sum. So this n-dimensional sum becomes a one-dimensional sum at the top. And that's what makes this possible. That's what makes it possible to do n-body expansion at arbitrary n. Okay, and so now if you look at that expression, you extract individual pieces out of this. The step one is what is now in gray. That's basically a pooling operation, and it's exactly what deep sets do. Yeah. Okay, so you know, if you know invariant theory, you would say, yeah, of course, those are the power sum polynomials. We've been doing that for decades. So you can basically take the simply a sum over particles of your one particle basis functions, and these features, they are permutation invariant features now that completely specify your particle system. Right? This is it's not a basis, but it's a in a way a coordinate transform, if you wish. It's a complete set of features. The next operation is what I put in yellow. We call this the product basis. We sometimes call this N correlations. We have many different names for that. And what these objects are, they are now really a complete basis of permutation invariant functions. So the precise statement is that if the one particle basis, the basis for one particle function, is actually a basis for one particle functions, right? If you put a dumb basis in there, then of course nothing's going to work. But then this product basis will be a basis of multiset functions, in the sense that any smooth multiset function you can write to with an arbitrary accuracy as you let the correlation order n go to infinity and the polynomial degree. Yeah. Maybe so in a way, it's maybe a fun remark here. I'm not sure whether it's interesting for the machine learners. I said that this is essentially deep sets, right? So then what we do here is we take a polynomial of these pooled operations. That is really what this does. Deep sets require everything to not be a polynomial. Our proof requires everything to be a polynomial. So it's a fun discrepancy, but fundamentally this is a very similar architecture. Okay. Now there's a final missing ingredient in the story, which is these properties, the models I'm after, have this group invariance, right? So how do we build that in? And that's the last step now. And the idea is trivial almost, right? You have a basis of permutation invariant functions. You average it over your group, and you're done, right? So now you have a new basis, and you can expand. You can basically, what you can show with very little work is that that by replacing the non-symmetric with a symmetric basis, the error cannot go up; it can only go down. And that's why you can still expand these set functions in terms of this invariant basis. This is, as stated, this is only true if G is a compact group. If G is non-compact, one has to be more careful. But in principle, morally, it's the same. Morally, it still all works fine. Okay. And so the only question that's left now is, what do you do with this one particle basis? And that's closely related to that averaging, right? So in essence, what you need to do is you need to choose a one particle basis for which you have a representation of the group. And once you have this, then the step from that basis A to that basis B becomes just a linear algebra operation, a sparse linear algebra operation. And so it even computationally costs you nothing to do this. Okay. So that is essentially the framework, right? And that's the framework of what we call the atomic cluster expansion. And you can now start playing with that, right? There are an enormous number of things you can do with this. Maybe, to make it concrete again, before I do go and play, is what does this look like for interatomic potentials, right? So now we have to specify what are our particles, and they will normally be pairs of relative positions and chemical species. Okay, what's the group now? Well, it's now the orthogonal group. So I can make this here concrete. Okay, now I know what the group is. I now know how to choose the one particle basis, right? I will use YLMs that gives you the irreducible representation of the rotation group, meaning this operation here becomes as sparse as possible, but you don't have to, in fact, right? So for example, if you use real spherical harmonics instead of complex, you'll get something that's I think that's not actually reducible anymore. anyways, it gets more performant. It gets you get so it's not necessarily the only choice. You can use different representations, and sometimes that's a good idea. But anyways, this is a canonical choice, and then all the other variables, right? So this is the angular component of the position. All the other variables, the radial component and the species, which are already invariant under your group action, you just dump into another embedding. And this could be a polynomial. That's why I'm writing Pn of R and Z. Yeah. So now we've almost fully specified this. We still have to specify the Pn. We'll get to that in a bit. And then here's your atomic cluster expansion model for interatomic potentials. Total energy is written as a sum over site energies. A site energy must remain invariant. That's what we've enforced here. And then through this ACE mechanism, you get a linear representation of these site energies. Okay. And in many ways, these are extraordinarily simple models. There are literally 4 operations you have to perform. Right, evaluate your embeddings, pooling, products, and matrix vector product. Yeah, I would say they're at least as simple as MLPs, maybe even simpler. Yeah, and there are fewer freedoms, fewer things you have to pick well. Okay, so I want to talk very briefly about the main theoretical results we have on this so far, because again, use excuse, I'm a mathematician, I sometimes just play around with theory. And the first one is not just theory. I mean, this is important. These models are not just simple, but they're actually very, very performant. And so one way you can quantify that is the following. You can construct evaluation algorithms. This is not entirely trivial. So now this one has to think about a little bit, so that the cost of evaluating your model is essentially twice the number of parameters you have. And I'm writing parameters of A, and I can explain later what the difference is here. Yeah. But you cannot improve on this, right? So you must have one floating point operation to evaluate the basis and one to combine it with the parameters. I don't see how one can have any model that is more efficient in terms of relative to number of parameters, right? So this is something that I was very keen on. And so there's no dependence on correlation order in there, right? So that means if you go to higher correlation order, then you forget exponential scaling. You don't even get linear scaling with correlation order. It's a constant scaling, order 1 operations per parameter. Yeah. And then the second one is basically, okay, can we actually estimate how many parameters we need, right? And so this is something that I worked on with Geneviève Dusson and Markus Bachmeier. And step 1 in that is how do we estimate how many parameters we get in terms of polynomial degrees, right? So if we choose polynomial basis functions, and I haven't really talked about this yet, I wanted to show this before I actually show you how we choose the basis. If you choose polynomial basis functions, then you can interpret all of this in terms of approximating smooth functions with polynomials. That's where the degree comes in. And you can show estimates like this, that the number of parameters for the A basis, the product basis, scales in a certain way. You can estimate how many parameters you get for the invariant basis, scales in a certain way. The essential statement here is this is sub-exponential. That's the first one. Once you go super-exponential, your life becomes bad. But sub-exponential is really not terrible. And the second one is, again, there's no dependence on correlation order in here. So in principle, you can go to high correlation order without too much cost, right? So it really enables you to model arbitrary correlation orders. And then if you take this and you convert it into actual model error estimates, so these are idealized estimates. These are not the actual model errors that you would get after fitting, because they assume that you do the best you can. You have all the knowledge about the target model that you want. And again, this precise detail is unimportant. The important thing is that it's a superlinear rate, an explicit superlinear rate, again, without dependence on the correlation order. That's what I was after here. And maybe a fun fact, all of these results follow from an old paper of Hardin Ramanujan. It goes into number theory of all things, right? Okay. How much time do I have? At most 15 minutes, right? 14. All right. So I think if you want to know numbers, let me just skip this, and let me just make one quick comment that I'm hoping we can get to tomorrow. when you have many chemical species, all of these results become very poor. Then you get the exponential scaling back, and something has to be done. And so just a few days ago, really, we finished a preprint where we're trying to explain how this could be done. This is very much inspired by what the equivariant neural networks do, and I can say more about this later, but I won't today. So really, what we wanted to know is, can we build good models with that? And I'll show just a very, very small number of results here. So for example, this was a graph I started with. For example, can we beat gap, right? Or at least match gap in accuracy, but get the cost down? That's really one of the things we were after. And what you see on this one, sure, yeah. And there are many, many more tests like it, where we always take gap as our reference, right? So how the Gaussian approximation potentials that Garbacciani had developed in the past, and can we do at least as well or better for much lower cost? And this is something that I want to get to if I can manage. Can we build potentials that are so robust that we can even start sampling the configuration space so widely that we can produce phase diagrams? So for example, this here is a heat capacity curve, and you can see where it peaks. This is where you expect phase transitions. We have two solid phase transitions, and the important one for us is the solid liquid phase transition. And we, for some reason, it even matches experimental values. Don't ask me why, even though we're trained into DFT. Right? So this is matching a solid liquid phase transition in a 4-component alloy trained from DFT. The workflow to get to that figure is almost automated. There is very, very little user interaction in this. And let's see if I get to this. I'll skip that. Okay, so can I talk about this? Maybe. Okay, so there are maybe how do we build real models now? Very briefly, right? So everything up to here was just framework, and the results I just showed you in the previous slides, they required you to make some choices, and one choice is this one: which of these features do you actually keep, and which do you throw away? And the second one is, how do you embed the invariant components of your particle? Right? For interatomic potentials, the radial component of the species, and you know, I think if you think like a machine learner, you would try to learn both. Right? You wouldn't bother trying to do this a priori. I'm not, so I try to do it a priori. Right? And again, if you go back to the idea of a polynomial approximation, this one is kind of obvious because the target properties we're after are all smooth. They're all smooth functions in high-dimensional spaces, and there's a canonical choice here that you make, which is called the total degree. So when we construct these polynomial expansions, we limit them, but not by taking the maximum n and l channels, but the sums over these. And that can be justified very precisely through approximation theory. And in fact, the approximation theoretic results I showed in the past use that. Yeah. Okay, so that's one thing. And the second one is the embedding of all the invariant coordinates. And so, I mean, this now really gets into the minutia, I would say. And so I just throw this out quickly. And what are the main ideas? Well, for the species, we don't really know what to do, so we just do a one hot embedding for that, and hopefully that creates this bad scaling I mentioned, and hopefully we're going to get rid of that over the next few months. But then comes something that has worked really well for us, which is the first thing to say is we shouldn't work in radial coordinates. That's a poor coordinate system, and the reason is if you think of typical potentials, they look roughly like this, right? So you have this region where really most of the interaction happens, and then it decays quickly to something very small and smooth, and then you have this blow up. This is where everything interesting happens. And so we do is we stretch this out. You stretch out this region and you compress the space here, right? And so then if you transform these functions under the right sort of coordinate transform, they look much easier to parameterize suddenly with few basis functions. Yeah. So and then basically once we're here, we're in this not just sort of qualitatively but quantitatively smooth regime. You can use any orthogonal polynomial basis. We tend to use Legendre, but I mean, pick your favorite one really. And then there's one more thing. We then multiply that thing with an envelope, which sort of characterizes very roughly what's the function doing when R gets large and what's the function doing when R gets small. Because here we don't have data. Here nothing interesting happens. And so the reason I wanted to show that slide, even though this is really sort of elementary and anybody would sort of come up with this is what for me replaces the geometric priors of graph neural networks. So if you do graph neural networks, you know connectivity, et cetera, et cetera. That's my analog for that. This is how I in the ACE models how I put in geometric information. Yeah. And maybe there's more discussion to be had here whether this is enough or not. All right. So I did go much slower than I thought. So I will not talk about jet tagging unless somebody wants to talk to me about that afterwards. And we'll talk for 1 minute about the connection to deep learning. Yeah. So I keep advertising these ACE models as something that actually has worked really well for us in many contexts, but the reality is they absolutely do not beat the deep equivariant neural networks in terms of raw accuracy. Right. So for example, here you can see the numbers, right? So we had a factor 3 missing somewhere, right? In some cases it's better, in some not so great. And so one of the students I've been very happy to work with, he really pushed this idea: how can we use some of these ACE ideas and put them into these neural networks? And so this is sort of a highly oversimplified way for me to explain this in 2 slides, right? So what these, and specifically the most natural context is to think of message passing. So the way, what you do is you say, okay, I need to give my particles additional trainable features, calling them H here. So every particle indexed by I gets additional features which I can learn, right? And then in each layer, I improve these features. So I learn in the next layer, I learn new features from my old geometry, from my geometry and the old features. And you do this over several layers. And then once you've learned all of these features in the different layers, then you do a readout. And that gives you then the actual properties you're after. And so if you now do the following, if you're saying, so what are these messages from which you're learning these features? They're typically constructed as 2 correlations. Yeah, in the best models up until a year ago, I would say they're always constructed from 2 correlations. And I would say the only change we've made to this architecture is to say, let's make them n correlations. Right? So that's what the ACE machinery gives you. How do you converge a model with correlation order rather than with layers? So let's, instead of taking 2 correlations, let's take n correlations in those messages, and there you are, right? And so we've redone some of these benchmarks now with this new architecture. And if you also put the right equivariance in, those are now details that I haven't talked about. These are all 2-layer models, by the way. Then you end up getting best possible accuracy across all the other architectures we compared against, and the performance is really fantastic in comparison. Right? So much shallower models and putting more emphasis on each layer. There's another minor detail here, that a lot of nonlinearities are gone. Really, the only relevant nonlinearity left is the correlation. So this product base is the only thing you need. All other nonlinearities are not needed to get these results. Okay. Should I do a 5-minute quick version of this? Yeah. So this is now, it goes into something that is very much at the forefront of most of our minds right now, that we have all these models and we're very happy with them, but it's still a big pain to actually collect training data, to tweak the parameters in the parameter estimation, until we actually end up with a model at the end that's really robust, right? This remains a huge pain. And so okay, if you want to throw most of that away, one way you can go with that is active learning, right? So you during a simulation, you attach an uncertainty estimate to your model. I know people here are very interested in this, so I wanted to at least briefly mention what direction we're going with this. And then the moment your uncertainty estimate goes above a threshold, you turn on your DFT model again, your reference model, and you collect more data because you've just found new data that where your model doesn't make a good prediction. You refit, and then you continue with your simulation. Okay, so that's fine. You can do good things with that. And these linear models that we have, atomic cluster expansion, also moment tensor potentials long before us, they have the enormous advantage of the linear models, and so you can get these uncertainties seemingly in a rigorous way. I mean, I'm saying seemingly, I'd love to have a discussion about that tomorrow, but there are caveats with that. So in fact, we don't do quite that. This gets expensive. We use committees instead, but you can take the posterior distribution and sample from that to get very good committees. So that's a minor detail maybe. And I'm saying seemingly also these are good estimates because they're not that great really, right? So you want really this cone here. So here you have the predicted force error. Here you have the actual force error on one specific example. You want this cone to be more like this here, right? Not like that. And so I'm very uncomfortable with that. And I'd love to learn how to improve this. But they work reasonably well as error indicators. So for example, here we're using this to filter a training set. We take a large training set, and it's actually not that large. It's already been manually filtered quite heavily, but then really we go down to 5 to 10% of that training set and get full accuracy on that. So they are quite good at telling you, is this a new configuration that you haven't seen yet, or do you need to add it to the training set? But the problem that I have with active learning is that it are rare events, right? So if you do molecular simulation, you always have rare events. They're always you're constrained to a small configuration of phase space, and then suddenly you go somewhere else, right? And that could take a very long time. And what I really prefer is having models where I don't have to give a user the new model and the DFT code coupled to it, and they have to keep going back and forth between that, right? You want to produce a model once and for all, put the parameters in a file, you download that, stick it into LAMMPS, and everything will just work, right? That's really our goal. And so towards that, this is sort of the very simple idea we came up with, not the first ones. I mean, the basic idea comes up in various different contexts, to bias the molecular dynamics towards high uncertainty. That's what this does. So you run molecular dynamics simulation, but you add a biasing term that drives it towards regions where your potential hasn't been, basically. That's what this means. And doing it this way, what this means is you're balancing the physics, that part, with finding new structures. So you're exploring configuration space, not too wide, not too crazily, but you're exploring parts of configuration space that are important. At least that's the intuition, right? How to formalize, how to make this rigorous, I don't know. Right? So go along in your MD, and then you go above threshold, go above a tolerance, you add training, you add more training data. So the idea is the same, but now you do this offline, right? So you do this before you finish your model and give it to a user. And well, I should stop here, but I think maybe I can only say it like this. If you do this iteratively, right? So you run this hyperactive learning dynamics, what we call it, until it breaks. You retrain, you do it again until it breaks. You train. Right? You see that you run for longer and longer time until you pass these thresholds, and so it takes surprisingly few iterations. So there's something missing in that third graph here. I need to check what happened. It takes surprisingly few iterations to get a robust model. So this is an example that we wrote here for aluminum silicon, 10% silicon, an alloy, right? And so with that process, you get very accurate predictions of melting temperatures, almost fully automated. The only thing you do is you give that HAL algorithm a few initial structures to very roughly sketch out the potential energy landscape, then you turn it on and it does the rest for you. Yeah. And there are many more things to say. I'm really sorry that I cut it so close here. So I do want to stop here, and I'll I'll be very happy to chat in more detail about any aspect of this. Thank you. All right, thank you.
Okay, yeah, so please. Let's go. Okay. Yeah, so any questions? I'll just pass around the mic and then we'll try to take questions online as well. If you can just type your questions in the chat or the Q&A box.
Thanks for the great talk. So I guess I have many questions, but I'll start with one and then give other people a chance. So in the ACE formalism, the thing that I'm typically predicting is something that doesn't have permutation indices. So it's usually like an energy or something like that. What specific aspects need to change if you do want to predict something that has like two-body correlation as in like the final tensor prediction?
So if you want to predict a tensor.
Yeah.
So I think, so first of all,
and just the, like what parts of the scaling change, and just to give a sense.
Okay, yeah, that's a very fair question. So when I talk about scaling, I usually talk about these estimates on how many parameters you get, right? Is that what you're after?
Yeah, I guess I'm just in this derivation, I'm just interested sort of at a first level, what are the parts that are going to need to change? Because I'm assuming that we won't,
all right.
we
So
won't be summing over quite.
If you want to predict it, if you want to predict a tensor, you basically change this step here. You will always go up to here.
But and this is if my indices of my tensor are permutation indices, not necessarily.
Okay, if they're permutation indices, you're asking now after a permutation equivariant tensor, right? That actually is a trivial consequence of this, because all you have to do, and that's exactly, by the way, what we do for wave functions. So maybe I can put that up, because then it becomes clearer visibly. Right. So this would be the scenario that you create an ACE model where you're highlighting one particle and have permutation invariance under the rest. So now if I swap out an I for something in here, that gives you the equivariance, the permutation equivariance. So we can write this down in detail if you're interested. But in essence, there is you have to parameterize one component of the permutation equivariant vector, and all the others follow. That's the gist of it. So that, and the way, roughly speaking, we can think about this is you add an additional imaginary species to the system, but it's simpler. It's a bit simpler than that. So yes, you get additional parameters because of that, because of the extra species, right? And we can, but it's not completely general, and therefore it's not that many extra parameters. And we can write down the exact number if you want.
In what sense do you mean it's not completely general?
Well, because you will need high correlation order in this part, but not here. This one comes up only once. And so you have correlation order 1 in that variable and correlation order n in those.
Okay, and this gives me something that just has a single permutation index. Yeah. And then is it straightforward to generalize if I want like a 2 or 3?
Absolutely. Okay. Any order you want. Yeah. And then of course I need to sit down and write down how many.
Yeah. But no, for sure. But just to get a sense for.
I don't see an issue with it. Let's put it this way. And if, I'm happy to write this down on a piece of paper. It shouldn't. In principle, this is very general and can be done.
Thank you.
My question is very simple. I didn't understand what is the total degree. So can you just explain again?
I went too quickly over this. Maybe I should do it somewhere else. Okay, so when you're parameterizing these pieces here, right? And in the end, that parameterization gives rise automatically through a bit of algebra to the ACE parameterization. You're specifying which tensor product basis functions you're taking, yeah? And so usually, if you don't think about this too much, then what you will do is you'll take a list of k indices, and then you take all possible n tuples of these k indices, right? But in high dimensional approximation, it gives you the curse of dimensionality. And so and what people have found is that when the target function is smooth, then you don't need to take all possible k tuples, but you truncate them in very different ways. The total degree means you truncate them in a simplex. There's hyperbolic cross degree, which means you truncate it into some other shape. So basically, you take different kinds of unit balls to tell you over which k tuples you're summing. And the total degree is just the canonical choice, in my opinion, and one can try others. Yeah, that's the vague answer, but do you want me to say more? Okay, say more. All right. So assume for a second that this is a one-dimensional variable, yeah, and k is simply the polynomial degree of that basis function. Then the total degree would be nothing other than the sum over k. Yeah, and one way you can think about this is, let's say this is an angle. These are trigonometric polynomials. That's a multivariate Fourier series. Then what I'm saying by saying I take a total degree, I'm saying that the Fourier coefficients decay exponentially fast. And that is exactly true when these functions are analytic. Yeah. So that's the connection. So if you have analyticity in this, then you know that certain parameterization have coefficients that decay exponentially fast, and you put this into your model by truncating that series, mimicking that decay of the expansion coefficients. Okay, so if you want to know why they decay exponentially fast, those are the...
No. Maybe I'll ask offline. I still don't understand.
I think I need to write things down to make that more concrete. But these are famous old theorems that, yeah. Pay-Levina theorems, that's what they're called. That's where this comes from. Yeah. And you can see how I'm coming from a totally different direction as the neural network people to this, right? Hi.
Hi, did I understand correctly that the ACE is less accurate than the deep learning?
Depends. Yes and no. So first of all, I would say which deep learning model? So TES's models, yes. I would say the NetQuip, which is based on E3 and N, that gives you, depending on the application, gives you quite much better accuracy at significantly increased cost. Yeah. So our models are much smaller, are very efficient, and that's what we need to do things like sampling. Right? So if you want to compute a phase diagram, you really, I suspect this would be hard with NetQuip, but has anybody tried? Yeah. So this is done on standard hardware in our case, in order of days. But also one of the points I was trying to make is once you take one of the key ideas in ACE, this correlation, and put it into NetQuip, well, the error goes down again, right, by quite a bit. So I try to emphasize that this is a general idea that you could again use for deep learning as well.
Yeah, interesting. Thank you.
Okay.
We should probably take any more questions offline. So, thank Christoph.
Thank you.